Colloquium speak Samim Akhtar. So he just, 1 month ago, almost.
1.5 months.
One and a half months ago, he arrived straight from Chennai, where he finished his PhD at the Institute of Mathematical Physics. So, and now he's starting a postdoc to work in the gravitational wave group. And so, basically, the idea is that to bring his mathematical knowledge to the phenomenology of gravitational waves. And as a start, the direction of his project will be clearer in 1 hour. Please.
Yeah. Hi, everyone. I am Samim, and thanks for the introduction. So mostly I will summarize my research area that I have been doing in my PhD and currently exploring here with Ricardo. And it's basically mostly on the broad area of gravitational waves, of theorems, etc., the various tools that we use in computing various classical observables that we can actually measure. And will not traditionally solve using equations of motion, but we will see how such things can be computed from the perspective of scattering amplitudes in QFT. So as we know that this the detection of binary black holes and neutron star mergers by the LIGO-Virgo-Kagra collaboration has recently, there is a renaissance in computing these various, in solving the gravitational two-body problem and computing theoretical waveforms to high precision. I will define these terms. So one of the most useful and fascinating quantities is this waveform that is basically the gravitational radiation at a distance of 1 by r, very far off distance from the Earth. And by that I mean that suppose there is we have to keep in mind that suppose we have a inspiral or scattering of binary star binary black hole, and the detectors are at Earth, so it's a very lights are very far off from each other, and we have these huge detectors in Earth, which are kilometers away. And what they do is that they basically measure the differential change in length of those two arms, which is known as the gravitational wave strain, and that is directly related to the metric perturbation that we have. It's basically a departure from the flat Minkowski background. So after the passage of gravitational wave, the length of those gravitational detectors oscillates a bit, and this is a very weak signal, but that we can compare with the theoretical waveforms that we have. So as a theorist, what information can we input? That is what the talk is about. So we have to before going further, we have to keep in mind that there are these 3 phases, basically what happens in the emission of gravitational waves from a binary black hole merger or a neutron star merger. The first phase that we have is this in spiral phase, where the 2 black holes are orbiting around each other, and then once they come closer, and then we have a sharp signal, which is the merger, it becomes a one compact object, and then we have this ring down phase. So in inspiral problems, since the 2 bodies are very far from each other, we can treat it perturbatively. We can apply some perturbation techniques, and we can consider them as point particles, because anyway, as observers, we are very far from the scattering setup. So these are the 2 approximations that are generally used to solve these kind of problems, apart from solving using the usual numerical relativity and using equations of motion. So the first one is the post-Newtonian approximation, which basically is the perturbation around Newtonian gravity. It specifically applies to bound orbits and generally applies to slow velocity. The other one is the post-Minkowskian approximation, which is where we specifically apply to unbound problems, like for example, 2 bodies coming and scattering off of each other. And there we have unrestricted speeds, but anyway, the gravitational, it's a perturbation, so it's the usual perturbation that we have in the QFT. So in this colloquium, I will mainly focus on the second one, post-Minkowskian approximation. I will talk specifically about the unbound cases, but there are various dictionaries which one can relate from the unbound problem to the bound ones. Yeah, so why amplitude? So computing this waveform field is intrinsically very difficult due to the existence of various scales that we have between the 3 phases. But since we'll be focusing on inspiral phase only today, where we can treat them as a point particles in the context of EFT. So there, it has been shown that amplitudes method is actually demonstrating its potential over the usual classical tools. And why amplitudes? Because amplitudes are, so what do we mean by amplitudes? So amplitudes gives you the transition probability from going from one state to another. And these are gauge invariant objects. So there will be various redundancies involving in the usual way of computing, like solving equations of motion. But since amplitudes are gauge invariant objects, we will treat them if we work with amplitudes, then they will give you directly those gauge answer, and there are no gauge dependencies for that. And so now what we can do, since we treat black holes as particles, we can now actually use tools that have been developing in particle physics, and we can directly use those tools to streamline gravitational wave computations. And this is so there are very advances in particle physics community. For example, we can now use these methods like unitarity cut, integration by parts reduction, and so on, double copy relations. I will define these terms, and soft factorization theorems, etc., which are used in various amplitude calculations in gauge theories and gravity to problems involving black holes. And so there are various ways to do it. So one of the most potent formalisms to generate classical observables directly from the scattering amplitudes is given by a seminal paper by Kosover, Maybe, and O'Connell. It's usually known as the KMOC formalism. So what is this KMOC formalism? These use scattering amplitudes as an ingredient to compute a set of asymptotic quantities, and we will be interested in classical values of those asymptotic quantities, and those will be our observable that we actually measure. And as I said, that in this talk I will be focusing on the unbound problem. So basically, we'll keep in mind that there we'll only consider scattering of two objects. It's a 2-2 scattering, and then we will see if there is gravitational waves emitting or the other. Then we'll see how the amplitude works. We'll also discuss how these various other tools like soft factorization theorems is used in the context of scattering amplitudes, and which reveals universal features of this gravitational radiation, such as the memory effects. So this will be my overview of the talk. I'll first introduce what this KMOC formalism is, and I will also discuss the advantages and over the usual classical tools, and then I will discuss some results, and about the soft factorization theorems, how is it universal in the context of gravitational radiation. And there is something interesting, which is the infrared triangle, which I will be discussing, and then we'll finally some conclusions. So we have in mind that we want to solve those classical observables directly from amplitudes. But prior to KMOC formalism, there were already have been hints that one can actually compute the corrections in the Newtonian potential directly from amplitudes, and loop amplitudes also do compute classical potential, and we will see how loop amplitudes contribute. So KMOC formalism is a framework to compute these observables, such as the scattering angle, if you're interested in what is the scattering angle in the 2-2 scattering, and radiative flux carried by the electromagnetic or gravitational amplitudes in large impact parameter. So this is very important because the two bodies are itself very far away from each other, and we being as observers are also very far from the center. So it's basically, this is important because that is why we're able to treat it as a perturbation. And what is the basic idea behind this formalism? The basic idea is to take wave packets for incoming classical particles. So now will be restricting ourselves in a QFT, but how do we model such particles to describe some classical scattering process? So that's why we'll choose wave packets for such incoming particles, and those will be very sharply defined to their classical values. So you can imagine that, okay, we'll label them as wave packets, but it's mostly a delta function, let's say. It's sharply picked around the classical values, and we will usually, and we treat simply, we'll study that the evolution, we will evolve those operators. Suppose, so here I have the basic defining equation. By delta O, I mean, if we're interested in, let's say, in computing the observable, let's say we're interested in computing the change in linear momentum of one of the particles in the 2-2 scattering. So how do we do that? So by computing the change in linear momentum, we essentially, this O operator will be our usual linear momentum operator. And we, given in a S matrix setup, we study the evolution of this operator, and we want to find the change in the eigenvalue of this expectation value of this operator. And this is the first line of this equation that is highlighted here. And this psi in is actually a 2-particle state because we are using 2-2 scattering, and we'll see how this describes the evolution. And now we use the usual trick that we use the unitarity property of the S matrix, which is S dagger S is equal to 1, and by S is equal to 1 plus IT, where T is the transition matrix element that takes you from one state to another, which is the usual amplitude language. And yeah, so now what the essential idea is that, so we'll study this evolution, but it sums over all possible outstates. So given an in state, we don't know what the outstate is. We want to determine the outstate. And instead of solving the equations of motion, we'll do this with amplitudes. So here it integrates all possible values of those outcome values and gives you the answer. Yeah, so as I said, that is the incoming two-particle state. And from here, you can see that the values that you have, it's sharply defined around those classical values. For example, this pi that I have, pi is a linear momenta. It will be just the classical value, and the deviation from this classical value will be of order h bar, which will treat it as quantum correction. And since we are in the regime of large impact parameter scattering, and so the change in momenta will be also very small. So we have the initial momenta of the scattering, let's say as pi. The final momenta will be small because of this large impact parameter. So essentially, it's a very small deflection scattering. So this is the thing that I have here, that the initial value, the impact parameter is b. So as b tending to infinity, it's a very small change. And how do we parameterize that? So if you look at the two-particle incoming state that I have defined here, so once you insert in the first line of this, second line of this equation, you will get everything in terms of amplitudes. By amplitude, I mean suppose it's a sandwich between the transition matrix of two operators. And in this KMOC formalism, this is important that we don't set h bar equal to 1 here. Like in the ordinary QFT language, we keep h bar as it is. And it is important because we see how do we parameterize by those the change in the moment of those values. So, and we also see that the various couplings that are involved in the theory. For example, if we restrict ourselves to electromagnetism, then the electric charge will be also scaled by E by root over h bar. And we can do this because, so there is this various Compton wavelength associated to this various particles. And the wave packets that we choose, we have to ensure that the spread in the wave packet is also small so that they don't interfere. It is very sharply defined. So basically this inequality that we have here, where LC denotes the Compton wavelength, LW denotes the spread in the wave packet, and B is the impact parameter, which is spatial. So this criterion itself suggests that, okay, we can take those wave functions and compute the amplitudes. So let's say if we want to, this is an example, let's say we want to compute the change in the linear momenta of the particles during evolution. That is known as the linear impulse. So how do we do this in the usual context of classical physics? So we have in mind supposed to choose two charged particles, and we want to study the change in linear momentum. We can do this by solving the Lorentz force equation, right? But instead of doing that, we will now see how it appears in the form of amplitude. So we just study the evolution of this. We just study the evolution of this operator where we set O as the linear momentum, and if we insert all those into incoming particle states, and the change in the observable, which is now delta P1, will be this quantity. It looks messy, but it's an interesting property that the first line that we have in this red color is the diagram on the left. So it basically denotes a 4-point amplitude because we have two particles coming in, two particles going out. And this is just the usual 4-point amplitude. And this is written to all orders in perturbation. So A4 is not just the tree level. We have a blob here. So it's a tree level plus one loop and so on. And the second term, which is in blue, because this comes from the second term here in the second equation. So it is a quadratic in transition matrix element T. So it cannot appear at tree level, but it is from one loop onwards, which is the second diagram. So once you compute these amplitudes and substitute in these equations, you can directly compute the change in the expectation value of P1. So now we see that as we proceed, this will be so only the 4-point amplitude is an ingredient for computing the impulse. Similarly, if we are interested in computing the gravitational radiation, then we will see the two particles coming in, two particles going out, and some radiation will be emitted out. And basically, it will involve a 5-point amplitude now, and which is the diagram here. And these two are the observables that we focus in this talk. Yeah, sure.
Right? So if you go back one slide, this is the usual in-out amplitudes, right?
No, this is not the in-out. Because in-out, we already know the in-state and the out-state. We don't have to integrate here. But this is the in formalism. By in formalism, basically, we're integrating all possible out-states. So we don't know the out-states. So by these amplitudes, where we have the P1.
But the four states that you have in your amplitude, I'm sure I'm confused about this, but the four states that you have in your amplitude, they all have different momenta, right? So if saying 2 to 2, shouldn't, if you're saying in, isn't it imply that you calculating the eigenvalue of your operator in the same state? So the two states on the left of the diagram should be the same as the two states on the right.
Exactly.
But why the momenta is different then?
Yeah, it's different because we are integrating all possible values of Q. So P1 plus Q is not our final momenta, but those are the conjugate momentas. We'll integrate all such possible values of Q. For example, if you look at the first equation, it is integrated over Q. So it's not in-out formalism, it's in-in formalism. Because given the in state, we want to determine what is the out state now. And But this is not the out final momenta. We are integrating over all possible values of Q, not with a fixed
It's
Q.
not fixed Q, okay.
Not fixed Q.
So the name comes from the fact that you impose all initial conditions. You don't, that's why in.
Yes.
So you impose position and velocity.
Condition Q is 0, right? For the initial condition.
Yes.
Yeah, and here Q is very small, as I said, because we are restricting ourselves to large impact parameter. And both the ingoing momenta and the outgoing momenta, they are very sharply picked and very infinitesimally different from each other. So that's why P1 plus Q is P1 is actually infinitesimally related, but then we integrate all possible values of Q and then compute the change in value of the. Sorry. Yeah, so for the linear impulse, we see that the 4-point amplitude is serving as an ingredient. Similarly, if we want to compute the radiation emitted in such setups, then 5-point amplitude will be enough. But naive question might arise, like, how do we incorporate, like, why such loop diagrams are contributing to classical physics? Because generally we know in QFT that only tree level consists of classical, and by loops we mean quantum corrections. But it's not the case here, because if you think that we are restricting ourselves to large impact parameter, so that means we are interested in the long range physics. So whatever we read in QFT, those basically deals with optional momenta, and those are actual true quantum corrections. But some classical contributions can also arise in the loops if you are interested in long range physics, those IR contributions. And how does KMOC take care of this fact that all the Q's, the massless momenta that we have, and the loop momenta as well, will scale it with H bar, because it's a very small quantity as we are restricting ourselves to large impact parameter. And this alone criteria takes care of the fact that you can see now that some classical contributions will be coming from those loop diagrams. And the remaining, all the region beyond H bar Q will be true quantum corrections that we have in QFT. Yeah. So basically, we can think of it as like that tree level classical by means that it just denotes the exchange of a long range field, because when we have a 4-point amplitude from 2 particle to ingoing to 2 outgoing, it just involves an exchange of momenta. That is the classical tree level. But the loop level classical, we can think of it as some in the context of some bond series. Let's say that the fields going have some back reaction, it's some radiation. So that is those are the terms that gets contribution from loops. Yes.
We have no linear self-scattering effects, and that's the kind of thing you're capturing.
Yeah, but
it's coming through the loops. That's kind of odd, that it's the loops that are introducing this. But in the end, that's what you're capturing, right?
Yeah, but it's not necessarily nonlinear. So in the context of gravity, of course, those nonlinearity will be captured. But even if we restrict ourselves to electromagnetism, so what happens is that suppose if you want to compute this delta p, the change in linear impulse, in usual classical physics, it just gives you, suppose if you add linear impulse of particle 1 plus particle 2, it will not be conserved. And then you introduced Abraham-Lorentz force by hand. That is the radiation reaction. But in this type of amplitude diagram, since we are starting from a unitary theory, every term is there. So those are those ALD terms are captured by those loops. So it takes care of all such ALD forces, both in context of nonlinearity and gravity, as well as some linear response in electromagnetism. Yeah, so as we saw that loops do contribute to classical physics for the long distance propagation. And suppose if we restrict ourselves to one loop, So these will be the relevant diagrams that we require for computing such potential or radiation. But the last diagram don't contribute here. So one can actually check explicitly scaling all the H bars, so like all the massless momenta and the loop momenta and with H bar. And and one can derive a general rule that there has to be some one matter line. There has to be some one matter line in the loop. Otherwise, it will be a purely quantum contributions. So for example, these box diagrams or the triangle-like diagrams will contribute to long distance physics, but the last one won't contribute. And this is the one that I told that once you have a massive momenta in your loops, only the classical region which is like on shell, those will correspond to those KMOC will capture those such regions. The rest of the regions are actually quantum contributions. And the power of this formalism is that this classical limit is taken as early as possible. So this is a really huge advantage of this KMOC formalism, that one will think that, okay, why not solve classical equations of motion, but loop diagrams will be difficult to solve. But it's not like that. We don't need to consider all the Feynman diagrams. As we can see, we can already isolate one such diagram. So the number of diagrams are less now. And also, you don't need to evaluate the loop integration completely, because only you need to pick out regions, and that region is already dictated by KMOC, that you scale all loop momenta and your massless momenta with H bars. And even before doing the full integration, you just take the H bar into zero limit, and you solve only a particular integration region. So things are quite simplified than the usual QFT amplitudes. And another advantage which I mentioned in the beginning, that it already captures the various radiation reaction effects that usually in classical physics you have to provide by hand, like the ALD force, or in context of gravity there is this Misa-Takua cell force equations, just the analog of ALD force in gravity, but you have to supply it by hand. But in this KMOC formalism, since it is built out of some quantum theory and unitary theory, every term is there. And we can isolate such terms, because you remember there were two terms while studying the evolution of this operator. One of them was the usual conservation of momentum. The second one, which was quadratic in amplitudes, like suppose if I go back and in the second equation, so the first equation will kind of capture conservative regime. And the second term that we have, which is the quadratic in T, those terms will capture those radiation reaction force, all the ALD forces. Yeah, so this is just whatever I said in words is just this equation, that it is automatically guaranteed that that the linear momentum is now conserved, taking into contributions of those radiation reaction effects. And so this is the usual KMOC approach. So whatever you have observable in mind, so I just illustrated here with an example of change in linear momenta, but one can also compute various things. Suppose if you want to compute the change in angular momenta of the particles undergoing scattering, or let's say you want to compute the radiation flux obtained by this setup, you can do that. And essentially at the end, you have, as early as possible, you take the H bar genetical limit, and it is done. And so after this, what happens that, so people now realize that this KMOC formalism is very powerful to compute these classical observables directly. And there are these various interesting objects that there are these various classical solutions relating one another. So for example, in this cuboid, I think it's visible here. So in the cuboid, suppose if, so I talked about a setup where we have some charge scalars, point charge, and that is usually the Coulomb charges. But suppose there are these additional things that if you apply electromagnetic duality, then you will end up in some different objects. By these classical objects, I mean these are some classical solutions of same theory or different theories. And so these are the three set of operations that we have. So on the z-axis, if we go, there is something called double copy, which relates gauge theories to gravity theories. I will elaborate this in more detail. And on the x-axis, you can see that there is this spin transformation, like it takes you from scalar solution to some rotating solutions. Like for example, if you have a Schwarzschild black hole, there is actually some complex coordinate transformation that you can do to this metric to land up in a Kerr metric solution. So this was way back in 1970s by Newman and Janis, and it is called as a, now it is used as an algorithm. It's called the NJ algorithm, where you generate some rotating solutions from scalar solutions. So for example, in this cuboid, if you see that if you go from Coulomb solution and you apply this Newman-Janis, you end up something called a root Kerr object. What do I mean by this root Kerr object? It is essentially, For example, as the so it is just the no-hair theorem analog, but in the context of electromagnetism. By no-hair theorem, I mean that all the black holes, externally the black holes can be treated as a point particle, and only charge, angular momentum, and mass detail are the three parameters that characterizes this black hole. That is the no-hair theorem. But similar no-hair theorem objects can be constructed in the context of electromagnetism, and those satisfy the usual Maxwell's equation, and that is the root Kerr object. And this root Kerr object can be directly obtained from some NJ transformation to the Coulomb-like solution. And there is this nice double copy relations in the context of amplitudes by this was long back in 2011, I suppose, that so the gravitational amplitudes can actually directly be obtained by some squaring of gauge theory amplitudes. So this is actually a very powerful tool, because we know that solving that when once you use the Feynman rules in the context of gravity, those are very messy, because there are many self-coupling terms like the 4-point graviton vortices. It's very complicated. But in certain gravitational amplitudes that we are interested in, you solve the entire problem completely in the language of gauge theory, and then you do a double copy like thing, which is this equation, the gauge amplitude times square, and you will end up in a gravitational amplitude. So this is remarkable actually, and we don't have such all loop order proof, but at least I know that two loops or 3 loops, it is guaranteed that this trick works. And so this root Kerr is actually a single copy of the Kerr metric. That is why I say that is the no-hair theorem analog of Kerr black hole. Yeah. So this was just the relation of between classical solutions, that various transformations you end up in various classical solutions. But how do we utilize this information? Because since we want to construct observables in amplitudes program, so how do we incorporate such transformations in amplitudes? So there was this beautiful set of minimally coupled 3-point amplitudes. So what we do is that when we try to compute amplitudes, the usual way we do is that we have some Lagrangian of a particular theory, and then we isolate the 3-point vertices or the 4-point vertices, and then we write down some Feynman rules and compute amplitude. But then there is a huge potential now with on-shell amplitudes. Like you start with a building block, you have some minimally coupled 3-point amplitudes, and you generate higher point amplitudes by some recursion relation. So in 2017, this Arkani, Hamed, Huang, and Huang, they have this minimally coupled 3-point amplitudes, which are where the external particles are massive, and but with the massive spinning particles. Those are spinning particles. So it's not restricted to some fermions or spin 3/2 or some discrete spin, but it has some dependence on general spin parameter S. So you have those amplitudes. You start with those basic building block amplitudes, and then you see that how these can this Newman-Jenisch algorithm that takes you from a spinless solution to a spinning solution, can this be manifested in the context of amplitudes language? And when this program started, so these people did not have such motivation of black hole physics as far as I know in their mind. But luckily, it turned out like after a year, once you take these amplitudes and you do some h bar tuning to 0 limit like KMOC, and you also take the infinite spin limit of those particles. So you have some expression of amplitudes which is dependent on S. You take some infinite spin limit. That is actually corresponding to some stress energy tensor contracted of a Kerr black hole contracted with an on-shell graviton. So those amplitudes are actually very, very useful in computing, in describing the classical black hole. And these are the 3 points. Since the expression involves some various notations, which will be difficult to explain in this talk, so I just wrote down the expression of, I just usually denote this 3-point amplitude as some A3 scalar. And as you can see that between these two equations, you see there is a nice squaring relation of the usual scalar 3-point amplitude. Like suppose if you have 2 particles going to 2 particles, this 4-point amplitude, you can build using this 3-point amplitude by the usual Feynman rule. And you can just naively apply the scalar QED Feynman rules and compute such quantity. And you do the same with Einsteinian gravity. And you will see that those two relations hold actually. So this is very powerful. Here A2 denotes the ring radius of the Kerr black hole. So this was just manifested by when we took the S tending to infinity limit of those amplitudes that Arkani, Hamed et al. Gave us. So this exponentiation that we have here, the e to the power q dot A2, this is actually the manifestation of the Newman-Jenisch algorithm that we had in classical solutions connecting one object to the other. And using this, we were able to actually compute the change in the linear impulse of the Kerr black hole to all order and spin. So this is a very powerful result. So it's not just some perturbative order in spin that we usually do in effective field theory, but it's an all order and spin computations, because now you can utilize those transformations in the amplitudes, and it takes directly from scalar solutions to some rotating Kerr black hole. We did this for root Kerr object because that was easier, because electromagnetism is always easier to handle than gravity theories. And the first equation that I have is the change in linear impulse. So here A is the spin, and it's an all order answer. And the nice manifestation was that when we had the usual coordinate transformation from the scalar to the from the Schwarzschild to the Kerr black hole metric, but in the context of amplitudes language, what it turned out beautifully is that it's just the impact parameter just gets complexified. So it's the usual trick that you apply a complex coordinate transformation to your impact parameter, and you will end up in the all order spin answer. And similarly, what we do is that since this is for the root Kerr object, one can actually directly apply this double copy, and this is a very powerful result now. And this directly gives you the answer for the Kerr black hole. So we utilize this Newman-Janice algorithm that we had in amplitudes, and we try to compute other such observables which are useful in the context of LIGO. Those are the various radiation flux and so on. And but this computation was done only from the tree level contributions. But it is important to understand how such Newman-Janice techniques can be manifested in the context of loop amplitudes language. So in the loop amplitudes, it's not very clear, but since we know that the relationship between the Schwarzschild metric and the Kerr metric, that is non-perturbative. So these relations must be utilized also in the case of amplitudes. And yeah, so this was actually my sorry. So this was the first part of the talk, that how do we compute this classical observable for amplitudes. But now we study some different perturbation, different expansion, but we'll be using this amplitudes language, and that is the soft radiation. So what we see that in both post-Newtonian and post-Minkowskian expansion, we compute radiation either which was at very low velocities, like in post-Newtonian theories, or large separations, where with unrestricted speeds, like post-Minkowskian expansion. But then there is a different expansion which leads to the insights of gravitational radiation, and those are the non-perturbative relations. Those are known as the soft theorems. So what is the setup in our mind? That consider a detector placed at infinity, whose frequency band is in the infrared. So you have some scattering going on in a setup, and as the detector will be from the detector, we just want to capture the soft effects, like the low frequency radiation. And we will see that there are actually very nice universal properties if you are interested only in the soft radiation part. And we'll see what is the radiation here. So for a generic gravitational scattering, the leading behavior of the radiative field long before the emission of gravitational waves and long after the gravitational waves. So this is given by this radiative field. So this is basically like when the gravitational waves has passed through a detector, we want to restrict ourselves only to small frequency expansion of this radiative field. And computing the intermediate dynamics is very difficult. But only for the soft frequency, one can compute and see that it's quite universal, because these are the various classes of terms that you have now of the soft radiation. And these are categorized into various different kinds of families. Like, for example, the first term that we have here, where n equal to -1, is the usual, in the language of QFT, is called the Weinberg soft theorem. And since this is a classical radiative field, the coefficient of this term doesn't depend on the dynamics of your problem. So you start with a different theory, or you change your particles. For example, instead of scalar particles, or you take black holes or neutron star, it doesn't matter. The first term is always universal, and it is just a function of linear momenta and the linear momenta of the particles undergoing. And that is what the memory effect is in the context of classical relative physics. And how do we define this memory effect? Is that suppose what happens usually is that after the passage of gravitational waves, those detectors that you have, they slightly get shifted. it's a permanent shift, and that is what is known as the displacement memory. And the first term with n equal to -1 is actually capturing this memory effect. But there are these other subleading terms that we have that goes as a Lorentz expansion. Those are known as the tails to the memory effect and so on. The blue colored term that we have here is only specifically in d equal to 4, because as one can understand that these logarithmic terms can arise because you have this long range Coulombic interaction in d equal to 4 always. You cannot cut it off. There is always this long range interaction, and this is why those IR captured effects, IR phenomena terms are there. The rest of the black colored terms and the red colored terms are non-universal, but you can see that if you are able to compute finite radiation and you do a soft expansion, you will end up in such terms. So this is what I was saying, that with the definition of universality, like if a term in the soft expansion is independent of the details of scattering, then we say those coefficients are universal. And this is the definition of the displacement memory effect. And where the first term, so basically in the last line we have the first term is known as the linear memory effect, and the second term is known as the non-linear memory effect. So by non-linear, it is exactly the is exactly the terms where gravitational waves do emit radiation, and those are the terms. Yeah. So this universality of these coefficients is actually proved in a series of papers, that those coefficients are actually universal, and they did this by actually solving asymptotic equations of motion. So it's a very standard trick that you take box H min equal to 0, the usual vacuum Einstein's equation. You solve them, you take the matter side, everything to the right hand side, and you solve using retarded Green's function, and then you can actually prove that okay, there is such a family of such terms. And the interesting thing is that long back in these blue colored terms that we have for d equal to 4 was actually predicted from quantum soft theorems. So this was not done from classical soft theorems, but these terms were actually predicted from the quantum side, and then later on proved rigorously using asymptotic equations of motion. And recently there has been a conjecture that one can write down an explicit formula of all such universal terms. For example, in this slide where you have this omega to the power m log omega to the power m plus 1 kind of terms, so those coefficients are actually now conjectured to all orders in perturbation, but restricting ourselves to 2 scattering. Yeah, so these are useful in the context phenomenologically interesting observables, because memory effect is actually an observable because it directly relates to the shift in your detector arm length. But what is the interesting? One of the interesting things that I later found out was that there are these various terms that are known as the tail to the memory effect, which are the next subleading terms from n equal to -1. And if you write down those terms first and you restrict yourself to a merger problem, like binary black hole merger, then those tail to the memory actually vanish for black hole merger problem, but not for neutron star. One can show actually this by computing, but there is no, as far as I know, there is no physical understanding like why such miraculous cancellation happens. So this might serve as a probe in the context of LIGO, LISA telescope. Yeah, so this is the next term apart from the memory effect in d greater than equal to 4. So again, this is the linear part. By j, I mean the angular momentum of the particles undergoing scattering. And similarly, this is the nonlinear part where mu denotes the angular momentum flux emitted by the setup. So this is the next term, and it in literature is usually known as the spin memory. And from here, actually, we can see that all those terms that we had, so there can be an infinite tower of higher spin memories, which are various subleading to the first term. And these were all written down in the context of low frequency, but one can actually see like how such terms will be appeared in the context of retarded time, because the thing that we measure in LIGO, it's all given as a function of t, and one can actually directly see with the Fourier transform that the first term that we have log omega can come from 1 by u. By u, I mean the u is the retarded time here, and yeah. So the physical origin of all such logarithmic modes that are restricted to d equal to 4 is the long-range Coulombic interaction between the states. Yeah, and this was the story behind the classical soft theorem. Like there are these universal terms in the classical soft theorem, but how do we, like, is there a relationship between the soft theorems that we know in QFT, like the Weinberg soft theorem and so on? So you can see that, for example, if I have a, so if I have an n particle going to some m particle scattering, which involves, let's say, gravitons, or in the context of electromagnetism, some photons, then the soft theorem states that if you are interested in a low frequency expansion, and then the n plus 1th amplitude can be written as the n point amplitude without the emission of those photons or gravitons. And there is a nice factorization property. This is known as the quantum soft theorem, or the soft factorization theorems. So the first term that you have here is the usual Weinberg soft theorem. The second one is the subleading soft theorem. This was proposed by Cachazo and Strominger back in 2014. And so the soft expansion in the classical relative field was actually predicted by these terms here. And later on, when it was proved rigorously by asymptotic equations of motion, that such logarithmic terms are actually there in the soft modes. So in the context of KMOC, like when we construct classical observables directly from amplitudes, so we remember that the 5-point amplitude was serving as an ingredient in computing gravitational radiation. But now that when we employ these soft theorem tools, like suppose if we're interested only in the low frequency radiation, then this 5-point amplitude can actually be further simplified by using the soft theorem language and computed in terms of 4-point amplitudes. Yeah, and the logarithmic modes can also be understood that, for example, in d equal to 4, we know that the S matrix is IR divergent. So the Coulombic force is actually 1 by r distance. So we can, so how does it affect the trajectory? If you integrate it twice, then you see that it diverges logarithmically. So for example, in the formula that you see here, this is for d greater than equal to 4. But let's say we use this same definition and we compute the angular momentum. So the angular momentum is basically x wedge p. But now when the trajectory diverges logarithmically due to Coulomb-like interaction, so we see that the angular momentum also diverges. But this is just nothing. This is the manifestation of IR phenomena. But what we can do is that we simply, yeah. Sorry.
Yes. No, the logarithmic term in the last formula of the slide has a g in front, does it? Is it g to the 1, is it?
Oh, these logarithmic modes?
No,
yeah.
no, in the slides before. So, you see, there is when you integrate the trajectory after the scattering, you get the c mu log t. That c mu is of order g, is it?
Yeah, but yeah, it's of order g, and it will always be there. You cannot switch it off. So it's to all order in perturbation. These terms will be there. So for example, this b mu and p mu by m tau, this is the straight line trajectory. And once you go to some, let's say you are doing a perturbative expansion in the trajectory, then those will be given by the coupling terms that you, as you said, that it will be a deflection trajectory. But this term, you cannot switch it off for d equal to 4. For d greater than 4, there will be no such logarithmic term because there is no such 1 by r Coulombic interaction in d greater than 4. But for d equal to 4, this will always be there. So in order g square, g cube, every time this will be there. So that's why these blue colored terms that I have here, these start appearing in the context of gravitational radiation. Yeah. So what one usually does is that, so we saw that for d equal to 4, this angular momentum actually diverges, and there will be log t term as well. So how did these people predicted actually? So they just did a naive substitution that you take t, since the trajectory is in time domain, let's switch to frequency domain and just do a naive substitution where take the inverse of this t as omega. And that is how these logarithmic modes were predicted even in the frequency domain. But later then people actually rigorously proved and show that actually such logarithmic modes do exist in classical soft expansion of the relative field. Yeah. So that was about the soft theorem. But so this is a very powerful tool actually, as it relates n-point amplitude to an n+1 amplitude without the emission of gravitons. And the classical limit of n equal to 0 term, that the n equal to 0 term we had, n equal to -1 is the usual Weinberg soft theorem, and the classical limit is the displacement memory effect. So similarly, if we want to say that what is the classical limit of n equal to 0 term, then that is known as the tail to the memory term, and these have been proved rigorously by these people sometime 5 years back. But this is not the end, because as we saw that in the context of soft expansion of your classical relative field, there are infinite such terms, infinite families of such terms. So in the quantum language, only Weinberg soft theorem and the subleading soft theorem I understand, but then there are these sub to the power n leading soft theorems. So I just wrote down an equation here where the 5-point amplitude is built out of 4-point amplitude. So this S hat n is actually the usual Weinberg soft factor or the subleading soft factor, those factorizable terms. But beyond n equal to 2, so from sub leading onwards, those 5-point amplitudes doesn't actually factorize. So there are some factorized portions and some non-factorizable terms. Those non-factorizable terms are called the remainder terms that we have now. So we ask a basic question, like suppose now we understand what is the classical limit of this Weinberg soft theorem. It's the memory effect. So how do we understand the classical limit of such higher order soft theorems now, considering now that these terms are not factorized and we have some remainder terms as well. So this I was trying to look at this classical soft limit of those such higher order soft theorems. And the interesting thing is that these remainder terms, if you are interested in very large impact parameter, basically large impact parameter, essentially it's a straight line trajectory and some very small vanishing deflection, then all such logarithmic modes that I showed in the classical expansion will be captured by such, the remainder terms won't contribute to such logarithmic modes, and all the logarithmic modes will be captured by the factorized sum. So this is an important result, that the log terms can actually be, so you given an amplitude, if you're interested in low frequency modes, if you want to extract the non-analytic terms such as log omega in your soft radiation, then you just take the factorized part. You don't need to bother about the remainder terms. But this is just only for the limit of vanishing deflections. By this I mean that impact parameter is very large. If you are interested in some finite impact parameter calculation, then of course you don't have to work with 4-point amplitude. You have to explicitly compute the 5-point amplitude because there will always be such remainder terms present. Yeah, so this is just one can actually prove this by just restricting ourselves to tree-level diagrams in the context of Einsteinian gravity theory, and these are the various 5-point amplitudes that will contribute. So what you do is that there are two things that can be done from here. You just compute the exact 5-point amplitude, input it in the KMOC formalism, and compute the radiation flux emitted by such setup. Another thing you can do is that you just take you employ the soft theorem language and you work everything in terms of 4-point amplitudes. So you'll be able to actually extract out such remainder terms. And one can actually show that those remainder terms, if you take b tending to infinity limit or very large impact parameter, then those terms drops out and only the factorized part is enough to consider. Yeah. So there is this interesting thing that we saw, that if we are restricting ourselves only to low frequency gravitational radiation, then all those coefficients are universal, and those coefficients actually depends on the asymptotic charges. For example, linear momenta of the particles or the angular momentum of the particles or the spin, nothing else. So one must say that because such gravitational radiation can be, these are the massless particles and these follow a null trajectory, and so can we understand this universality only by studying gravitational physics at the boundary? So this is very striking because one might ask why such universal terms are there in soft expansion. And so there are these various classes of asymptotically flat spacetimes where if you are restricting yourselves to gravitational radiation, this actually falls off as 1 by r. So there are various classical spacetimes which as null infinity will give you the usual Minkowski, and those such spacetimes are known as asymptotically flat spacetimes. So now if you want to study this gravitational radiation in the background of this asymptotically flat spacetimes, we can understand this universality. And how is it understood? Like for example, at null infinity, the gravitational radiation usually follows the null ray, and is there. So the flat sphere metric, suppose if we write down the flat metric and use spherical polar coordinate system, let's say, so it will be a 2-sphere. And what we can show is that the flat metric written in this language, once the gravitational waves has passed, we can understand that this metric will get disturbed, of course, and that metric is actually, for example, this QAB is the usual 2-sphere metric, so it gets disturbed by this CAB. Here CAB is known as the shear. So just as we saw phenomenologically that there are these two detectors, and once the gravitational waves has passed, there will be a very, the mirrors actually gets permanently shifted by a very small amount. So similarly, the matrix also gets disturbed, and in this language, this CAB is actually capturing the memory effect. So there is this nice connection that the classical limit of Weinberg's soft theorem is giving you the displacement memory effect, and one can also study gravitational physics at the boundary and see that the change in the CAB means the shear tensor, is giving you the memory effect. So there is this nice triangular relationship between these three fascinating objects, and this is basically known as the infrared triangle. So on one hand, on one side you have this quantum soft theorems or the factorization theorems. On another side you have this memory effect, tilts to the memory effect, and so on. And on the other side you study the gravitational physics and boundary, and those are the symmetries. Why symmetry? Because, for example, as we saw that, so the group that we have now, for example, these asymptotically flat spacetimes, at null infinity limit, these asymptotes to the usual Minkowski. But if you want to study these asymptotically flat spacetimes, you will see that the symmetry is enhanced from the usual Poincare symmetry to some BMS symmetry, where Bondi, Mason, and Sachs, they studied this. And so once you have symmetry, you can compute these Noether charges actually. And the symmetry, the usual translations and rotations are of course there from the Poincare group. But now since it is enhanced to a bigger group now, so you have this called, you have some general arbitrary translations called the super translations. So what you can do is that this retarded time that you have here, if you just translated it, of course Poincare symmetry is there, but now it has been shown that in this kind of metric, even if you do a general transformation of this U, not just translation, but any arbitrary function f on that two-sphere metric, and that will also give you a flat metric at the asymptotic language. So these kind of symmetries are known as the super translation. One can actually compute charges, word identities, and so on, and then show that explicitly it gives you quantum soft theorems like Weinberg's soft theorem. So this is just like well studied, and so there will be infrared triangle for each of such objects. For example, Weinberg's soft theorem, displacement memory effect, and the super translation. Similarly, there will be infinite triangles. For example, we have tail to the memory, we have subleading soft theorem, and on the asymptotic symmetry, we have something called super retractation, which I will be not talking about here. And then the people are now studying like this relationship like of higher order soft theorems. Like we understand up to subleading, but let's say what is the three-way relationship? Like suppose if I want to study tail to the memories, which are like further subleading in omega, but can we have an understanding from the asymptotic symmetry language? So there has been progress recently, but it's not the, it is quite remarkable to understand about the two all order interpretation. Yeah. So how much time do I have? Okay, then it's good. Okay. So we saw that unlike the usual path of computing the classical observable by traditional equations of motion iteratively, one can actually define these observables in the QFT sense and take a good classical limit like h bar tending to 0 in terms of perturbative amplitudes. And we saw that the power of KMOC formalism is that the classical limit is already taken as early as possible. So you don't need to solve all the Feynman diagrams that you have, and you restrict yourself to only classical regions that contribute to your classical physics. So, and all such additionally such radiation reaction effects are naturally inbuilt within this framework. And we also saw that there is this infinite tower of low frequency relative modes in such gravitational radiation, and these are non-perturbative because it holds to all order in perturbation. For example, memory effect will always be there even if you do a tree-level computation. It is exact to all orders in G. And these modes can be efficiently computed from the classical limit of quantum soft theorem. So this is the main ingredient. And we also saw that these asymptotic symmetries, various memory effects, and the quantum soft theorem are facets of the same IR triangle. As I was saying that this is not just the end. There are these various, instead of promoting from super translation, there is this super translation, and the group is called now generalized BMS group. So there has been work going on. And so one important thing was like in the context of KMOC, we restricted ourselves to large impact parameter scattering, but we just now saw that one can actually compute soft radiation, and that is non-perturbative. But can we now instead compute only, can we prove this classical soft theorem in the KMOC language? So this we have been able to show at least for the leading soft theorem. This will just come sometime, maybe next week or something, I don't know. And yeah. And there are various other things. For example, here, just like love numbers of black holes, as I was saying, that in a binary black hole merger, the tail to the memory vanishes, and it will be good to understand the gravitational physics or the symmetry behind this problem. And with Ricardo, actually, I was like, all of these I have been restricting myself to unbound problems. But let's say, can we build these bound problems from, study these bound states from amplitudes, or consider soft theorems for this bound orbit problem? With that, I would like to end, and this is just the flowchart that I have been drawing. There is a nice connection between this infrared triangle and the black hole physics and so on. Yeah, thanks for listening. Thank you.
So classical gravity is hiding more than we thought.
Yeah, this is all. Yeah, just to emphasize that this was all about classical gravity. Yeah.
Thank you. Could you please clarify the claim about the vanishing of tail of memory in the case of binary black hole? I think I don't understand, because in the context of classical calculation in GR using, say, post-Newtonian theory and multipolar post-Minkowskian expansions and so on, using two-point particles, so it doesn't matter whether you have black holes or neutron star, you do get memories, tails, and tails of memories. Mm-hmm. So I don't understand what you're referring to here.
This was just restricting ourselves to a merger. Like, for example, you have two black holes orbiting around each other, then you have one compact object. Only in such scattering setup, one can actually show that the tail to the memory term vanishes. Otherwise, if you have, like, for example, two black holes orbiting around emitting gravitational waves, or let's say if we restrict ourselves to some unbound problems from 2 to scattering, then those sub-terms will obviously be there. We will have infinite such tails to the memory. But only in case of merger, like, for example, when the final outgoing state is just one object, only in such type of terms, at least for the black holes, those tail to the memory vanishes. But if the gravitational waves emission is from a neutron star or a black hole binary merger, then those such terms don't vanish. So this can be a probe to differentiate between a black hole merger and a neutron star merger.
Thank you.
It's not, I mean, of course, it's not detected, it's, but from the theory, one can actually compute and show that this happens.
Okay, so if there are no further questions, we can thank Samim again.
Okay, thank you. Yeah.